I'll ground this in real reliability data before writing. Quick note first. There's no single 250,000-mile test that exists as one study, so I'll build the script around real longevity and reliability data, including IC Cars mileage studies, Consumer Reports reliability surveys, and warranty and repair cost data, rather than inventing one fake test. This is the same approach we used on the RAV4 Prime script. Here's what the data actually shows before I write this. I couldn't find a single 250,000-mile test as a real, one-time event. What exists is aggregate data from IC Cars' 2025 study of nearly 400 million vehicles, plus RepairPal's cost and frequency database. That's actually a stronger hook than a fake test, so I built the script around real numbers. Toyota has a 17.8% chance of reaching 250,000 miles, 3.7 times the industry average. Lexus has a 12.8% chance, and Honda has a 10.8% chance, versus BMW at 0.4%, Volkswagen at 0.4%, Audi at 0.3%, and Mercedes-Benz at 1.7%. Repair cost data backs it up. Toyota averages $441 a year in repairs, Honda $428, and Lexus $551, versus BMW at $968, Audi at $987, and Mercedes-Benz at $908. Here's the script built on that foundation. 2 customers came through my bay in the same week. One drove a BMW 3 Series with 91,000 miles on it, and she was staring at a 4-figure estimate for a water pump, a thermostat housing, and a batch of vacuum lines that had turned brittle. The other drove a Toyota Camry with 247,000 miles on the original engine, and she was in for an oil change and nothing else. Same decade of ownership, wildly different outcomes. And for years, that split has fueled arguments in every comment section on the internet. German engineering versus Japanese reliability, precision versus simplicity. But nobody was actually looking at the numbers until IC Cars ran the largest odometer study in the industry's history, analyzing almost 400 million vehicles to calculate the real predicted odds of any car reaching 250,000 miles. What they found didn't just confirm the stereotype, it quantified it down to the decimal point. And once you understand the mechanical reasons behind those numbers, the debate isn't really a debate anymore. Let's go through exactly what the data shows and exactly why it happens under the hood. Data point number 1, the raw odds. According to the IC Cars 2025 longest-lasting vehicles study, the average car sold in America has a 4.8% chance of reaching 250,000 miles. Toyota sits at 17.8%, nearly 4 times that average. Lexus, Toyota's luxury division, comes in at 12.8%, and Honda rounds out the top 3 at 10.8%. Now flip over to the German luxury brands. BMW comes in at 0.4%. Volkswagen, Germany's mainstream brand, also sits at 0.4%. Audi is even lower at 0.3%. Mercedes-Benz does noticeably better than its German counterparts at 1.7%, but that's still less than 1/10 of Toyota's number. This isn't a small gap. A Toyota is roughly 44 times more likely to see 250,000 miles than a BMW based on this data set. That's not marketing. That's odometer data pulled from real used car listings and registration records across the country. Data point number 2, what it costs to keep them running. RepairPal's database tracks average annual repair costs and how often a car ends up in the shop for something severe, meaning a repair that costs 3 times the brand's average annual cost. Toyota averages $441 a year in repairs, with a 12% chance of a severe repair in any given year. Honda averages $428 with a 10% severe repair rate. Lexus sits at $551 with an 8% severe repair rate, actually the lowest severity risk of the group. Now the German side. BMW averages $968 a year, more than double Toyota's number, with a 15% chance of a severe repair. Audi averages $987 with a 13% severe repair rate. Mercedes-Benz averages $908 with a 13% severe repair rate. So it's not just that German cars are less likely to hit high mileage. It's that getting them there costs roughly twice as much per year along the way, and the individual repairs are more likely to be the expensive kind rather than the routine kind. Now here's where it gets interesting, because the numbers alone don't explain anything. The explanation lives in the engineering philosophy, and once you see it laid out piece by piece, the pattern makes complete sense. Reason number 1, timing chain tensioner design. Toyota's naturally aspirated 4-cylinder and 6-cylinder engines, like the ones found in the Camry, the 4Runner, and the Tacoma, use a timing chain and tensioner system built with a heavy margin of safety, meaning the components are sized to handle far more stress than they'll ever actually see in normal driving. BMW's N20 and N26 4-cylinder turbo engines, by contrast, became infamous in the shop world for timing chain guides made from a composite plastic that degrades under sustained heat cycling. When that guide fails, usually somewhere between 60,000 and 100,000 miles, it can send debris directly into the oil pump pickup and cause catastrophic engine damage. Volkswagen and Audi's EA888 engine family has a similar reputation for timing chain tensioner failure, where the tensioner loses hydraulic pressure and allows chain slap that throws off variable valve timing. These aren't rare freak occurrences. They're common enough that independent shops budget for them as expected maintenance items on high-mileage German cars, which tells you everything about how the engineering margin was set from the factory. Reason number 2, the plastic coolant system problem. This is one of the most consistent failure points across German engines. BMW engines from the middle of the 2000s through the 2010s used a plastic impeller inside the water pump itself, along with a plastic thermostat housing and plastic coolant expansion tank. Under the heat cycling of normal driving, that plastic becomes brittle over time, and the water pump impeller can literally shear apart inside the housing, which is exactly what happened to my customer in the 3 Series. Audi and Volkswagen engines share this same design philosophy, with coolant flanges and thermostat housings made from a similar composite plastic that cracks under thermal stress, usually somewhere in the 60,000 to 90,000 mile window. Toyota's cooling systems, by comparison, still lean heavily on aluminum and reinforced composite housings in the areas that see the most heat and pressure cycling, which is a large part of why Toyota coolant systems routinely go past 150,000 miles without a major failure. Reason number 3, turbocharging and heat load. German manufacturers moved to small displacement turbocharged engines faster and more broadly than Toyota did, largely to meet European emissions and fuel economy targets. A turbocharger adds tremendous heat and pressure to an engine bay that was already tightly packaged, And it also means the oil is working harder, since it's now responsible for lubricating and cooling the turbo's bearings in addition to everything else. That shortens the safe interval between oil changes and raises the stakes if an owner stretches that interval even slightly. Toyota does use turbocharging now on select models, but the brand's reputation for longevity was built primarily on naturally aspirated engines that run cooler, see less thermal stress on the block and head gasket, and give oil an easier job to do over hundreds of thousands of miles. If you've made it this far, go ahead and hit that subscribe button, because I break down exactly what's happening inside these engines every single week, and it helps more than you'd think. Reason number 4, electronic complexity. Modern BMWs, Audis, and Mercedes-Benz models run dozens of interconnected control modules. Everything from adaptive suspension dampers to air suspension compressors to multi-zone climate control units, all communicating over a CAN bus network. Every one of those modules is a potential failure point, and German luxury brands tend to add more of them per vehicle than Toyota does. Air suspension alone, found on many higher trim Audi and Mercedes-Benz models, is a well-documented weak spot. The air struts and the compressor that feeds them are wear items, and by 80,000 to 100,000 miles, it's common to see a strut start leaking air overnight, leaving the car sitting lower on one corner by morning. Toyota, even in its Lexus luxury trims, has historically used more conventional steel spring and shock absorber setups on its high-volume models, which trade some of that adaptive ride comfort for a part that simply doesn't fail the same way an air spring does. Reason number 5, direct injection carbon buildup, and this one's actually more balanced than people assume. Volkswagen and Audi's TSY engines rely on pure direct injection, where fuel is sprayed straight into the combustion chamber instead of across the intake valves. That means there's no fuel washing over the back of the intake valve to keep it clean, and over 60,000 to 80,000 miles, those valves can build up a hard carbon deposit that restricts airflow and eventually causes rough idle and misfires. Toyota addressed this same physics problem differently on many of its models by using a dual injection system called D4S that combines direct injection with a secondary port injector. That second injector sprays fuel across the intake valve during certain conditions, specifically to keep it washed clean, which is a small design decision that prevents a very expensive walnut-blasting carbon cleaning service down the road. Reason number 6, maintenance accessibility and cost. And this is more about ownership behavior than pure engineering, but it matters just as much to real-world longevity. German vehicles frequently require dealer-level diagnostic software and specialized tools for jobs that would be routine on a Toyota. A spark plug replacement on a transversely mounted VW engine can require removing the intake manifold. A battery replacement on many BMW vehicles requires registering the new battery with the car's electrical system through a coding tool, because the battery management module needs to recalibrate charging behavior. That complexity pushes owners toward dealership service, which is expensive, and expensive maintenance gets deferred far more often than cheap maintenance does. A Toyota water pump job might run a few $100s at an independent shop. The equivalent BMW job, with its transverse engine layout and tighter accessory belt routing, can run well past $1,000 in labor alone. When maintenance is expensive, owners skip it, and skipped maintenance is where reliability data actually gets made. Reason number 7, design margin philosophy. This is the closest thing to a root cause behind everything above. Toyota's engineering culture, going back decades, has prioritized what's internally described as overbuilt tolerance, meaning components like bearings, gaskets, and mounts are sized to handle significantly more stress and more heat cycles than they'll realistically ever face. German manufacturers, particularly BMW and Audi, have historically prioritized performance and precision first, building engines and suspensions that deliver sharper handling and stronger power output per liter of displacement, often by running components closer to their actual limits. That's not incompetence. A BMW inline-6 making the horsepower it makes from that displacement is genuinely impressive engineering. But running closer to the limit on purpose means there's less margin left over when a part starts to age, and that shows up directly in the odometer data 30 years later. Now, a fair caveat here, because I don't want to oversell this. The iCar's data measures which cars are still on the road, and that's influenced by more than just parts quality. Ownership patterns matter too. German luxury cars are more likely to be leased, traded in at 60,000 or 80,000 miles, or sold once the factory warranty runs out, specifically because owners know repair costs climb sharply after that point. Toyotas are more likely to be kept by their original owner for a decade or more, or passed down within a family, specifically because owners trust them to keep running. Some of that gap is mechanical. Some of it is a self-reinforcing cycle where German cars get sold before problems appear, and Toyotas get kept because problems don't appear. Both things are true at once, and that's the honest picture instead of the oversimplified one. So what does this actually mean for you if you're cross-shopping a German car against a Japanese one right now? If you're buying a BMW, Audi, or Mercedes-Benz, plan your ownership around the plastic coolant components specifically. Have the water pump, thermostat housing, and coolant expansion tank inspected proactively around 70,000 miles rather than waiting for a warning light, because by the time that plastic actually fails, it often fails all at once on the side of the road. Budget real money for maintenance, not dealership sticker price money, but genuinely double what you'd expect to spend on a comparable Toyota, because the data backs that number up almost exactly. And if the car has air suspension, get in the habit of checking ride height in the morning after it's sat overnight, since a slow leak shows up there before it shows up as a dashboard warning. If you're buying a Toyota or a Lexus, the ownership strategy is simpler by design, which is really the entire point of this whole comparison. Stick to the recommended oil change interval. Don't ignore the timing chain if the vehicle happens to be one of the rare Toyota models that's had reported guide wear at very high mileage. And understand that the low annual repair cost isn't luck. It's the direct result of a company that has spent decades deliberately building in more margin than the car will ever need. At the end of the day, this isn't really about German engineers being worse at their jobs than Japanese engineers. It's about two completely different definitions of what a car is supposed to prioritize. One philosophy chases precision and performance right up to the edge of what the materials can handle. The other chases quiet, boring, predictable longevity, and accepts a little less sharpness in exchange for it. The data makes it clear which philosophy produces more quarter-million-mile survivors. What you do with that information depends entirely on what you actually want out of your next car. If you're enjoying breakdowns like this, the next video I'm putting out digs into exactly which specific components fail first on high-mileage German engines and what it actually costs to fix each one before you buy used.